I should put out the videos on YouTube. I should do a lot of things. But, well, if we start, so to say, where are we? Bhutan. Fresco. I think we are somewhere here. 10 o'clock. Is that a good time?
Yeah.
And then I suggest we go first to this salt lake. I mean, Värtan is the continuation of the harbor. So we take some samples, measure some pH, conductivity, temperature, etc., and note some parts that we can possibly correlate with the conditions that we analyze the water from later. Then we take a sample here. I don't know how to, they have put up a fence around some areas here, so it's difficult to get in touch with the water, but I try to find some possibility to take a sample. Then I suggest we walk to Ladeviken. To this side of Ladeviken, in fact, because there is a bridge here and it's very convenient. You can actually easily take the samples here. Here it's not at all as easy. And finally, I suggest we go to Brunnsviken and then back. How long this journey will take? I mean, it takes some time for each. We have 4 sampling positions, and it may take maximum. How long time does it take to fill a large flask and measure some parameters and do some observation? Half an hour or so. Some transport time. So I would say 3 hour total time, approximately. But I'm not sure. Anyone knows what kind of weather will we have tomorrow?
It's sunny.
Sunny? That's good.
Yeah, but cold.
But cold, yeah. So then you realize that you shouldn't get wet, of course. Kläder efter väder in Swedish, or clothes after weather in English. So keep warm and take some shoes that is easy to walk in. I mean, this is civilized country, so there are, for example, roads to walk on. You don't. It's far away from the situation moving out in the forest. But I see to that there are some flasks to fetch samples in. We should take a couple of different samples. I will show you what. No, let's see, where is it? It is in lab and it is in lab 1 review. We could, of course, do, these are quite many things. Some of them are more important than others, I would say. I would say that alkalinity and the calcium magnesium content, either you can determine calcium or the sum of calcium magnesium. These two relates to each other and they are important. Then chloride ions and sulfate ions are I would say less important, but of course not useless anyway. The organic carbon or the chemical oxygen demand, it's a measure of the organic compound content of the waters. We don't see the organic content, but it can anyway be there. So, and then we should determine oxygen concentration. This could also be done electronically, according to some old, I think it's a German guy, more than 100 years ago, Winkler, that devised a method for determining O2. So alkalinity is essentially, one can approximate it with the capability of neutralizing H+ acid. Alkalinity, alkali is sounds like basic. Alkali is synonym for a strong base, sodium hydroxide, for example, or alkali solutions. They are basic solution, and the majority of the bases in most natural waters are hydrogen carbonate. But it may be other elements also. We'll see. A way to investigate this is to do a normal titration, an acid-base titration of the content of basic ions. And you should determine alkalinity from all 4 lakes or all 4 sampling places, and then we should see if we can draw any conclusions regarding different lakes, and well, see any connections between different parameters. In literature, one has seen alkalinity determinations both within done with an indicator, a chemical weak acid that has different colors in acid or base form. If you would like to test it, I can arrange it. Please let me know in that case. Otherwise, I suggest we use a pH meter and get a curve, titration curve, to plot on paper. How do you plot curves, by the way? If I want you to draw a graph of a titration curve, is that done automatically, or do you want help?
For me, it was a long time ago, but I think I'll manage. Yeah. Maybe my brain will remember.
Yeah, exactly. Yeah, exactly. And the rest of you? Do you think you need to think, you don't have to make the titration curve directly, but as soon as on Thursday when we do the titrations, you can just take notes. So bring a paper and a pencil, or I can fix a paper. So, but bring a pencil. And then we discover what kind of problems that occur, what kind of software. Do you want to, I have millimeter papers. So if someone wants to draw them curves on millimeter papers, as we did in ancient time, that is also a possibility. Otherwise, I recommend some computer programs because it's less work. If you draw them literally on paper, then the first error you do, then you get a problem. calcium ion determination. That is, there are some calcium ions, probably, I hope, in the water sample. Some of the calcium ion complexes that we will find out now, they are colorless. For example, the pure calcium ion in water solution, that is colorless. And also we will add something, a complexing agent called ethylene diamine tetraacetic acid, or some salt of it. That is also colorless, so we won't see them. On the other hand, we will see some colored complexes, some colored compound, either an indicator that we add to the solution, but together with calcium ions, it will form a red complex or a reddish. The difference between the calcium indicator complex and the pure free indicator is far less pronounced than the difference between, in reality, it's far less pronounced than the difference between these two colors. I don't know if you are colorblind, then this is an impossible lab to do, but please tell us if you are colorblind, at least if you are colorblind to red and blue. Otherwise, take some help. You can work together in pairs or something like that. I sense that you are something like maximum 20 persons, so we could have the different labs at stations, and then we just swap people around the stations. There may be some problematic, some crowding around some stations, and maybe we can add more, but I think we can solve that. Adding the indicator to a water solution containing calcium ions will, as I said, produce a red complex, but adding then EDTA to that very same solution, here described by the capital Y, will break up this complex, and after a while all of the calcium ions will be occupied by EDTA molecules, which are colorless, and then the indicator will be let free, and that is bluish. This titration should be done at quite a basic pH. This is one of the risks with this elaboration, because basic solution, I think we have a 2 molar sodium hydroxide solution. And the risk with that is that if you get a drop in your eye or something like that, unless you rinse very fast, you will get hurt. But of course you can try to avoid getting chemicals in your eyes. I mean, you should wear some goggles, safety goggles. That is the most important part of the safety equipment on lab. Then comes the lab coat maybe, and perhaps also gloves, but I mean, there is no risk in this experiment so that you will need gloves. If you get a drop of sodium hydroxide on your hand, you will actually feel it, and then you know that you can rinse it off with water. If you get a drop of sodium hydroxide on the outside of a glove, you won't feel it. So you can scratch it off on your ear or something like that when scratching yourself in your head. And that will be less good, actually. Of course, it's only to rinse off. Put your head down below the sink and let someone help you to rinse off the sodium hydroxide. No one, we haven't done that over all years yet, but it's a possibility. Think about whether you need gloves or not. Gloves are used if you should avoid getting poisonous compounds on your hands. Otherwise, I'm not sure that they are any good. In practice, you do take the some sample water, add some indicator, you get a color, add some EDTA, measure how much EDTA you add in order to get the transition to blue. If this is not so clear, then it may be needed to be repeated. But I mean, this is a 5-minute experiment or so, so it may very well be repeated 1 or 2 times. Doesn't matter. And maybe you took quite too small amount of sample water, then it may need to have more sample water, or you may have to change the EDTA solution to a stronger concentration or a lower concentration or something like that. We'll see what problems that arise with the actual experiment. The calcium magnesium, the sum is very, very similar to the case with calcium only. The only difference is that we use another indicator and another pH where we do the titration at. So we'll use a buffer solution for obtaining this pH. I don't know if you remember buffer calculations, but all of the chemicals will be readily made. So in order to get a pH 10, we take some acid-base pair with a pKa close to it. For example, ammonium ion has pKa 9.3. So then we should have a majority of the basic part and a minority of the acid part, and then we will have pH 10 approximately. Chlorides. Moore is perhaps also a German guy from the past, probably more than 100 years ago. These chloride ions, one can determine them by adding silver ions, and then a white precipitate will have milky solution, so to say. This is difficult. The equivalence point is when you have added enough silver ions for no more precipitate to form. But how do you reckon whether you have a milky solution, a milk white solution, and suddenly it do not continue to be more milk white? This is hardly possible to detect. But if there would be another element also, chromate ion, this is an ion that you should avoid getting on your skin. If you do get it, then rinse it off with water. Otherwise, there is no risk. There's no risk of inhaling it or something like that. It's a water solution. But if this one is present simultaneously as the chloride ions, so when the silver chloride, that is the most insoluble compound in this case, when that has been formed and depleted the sample water from chloride ions, then the chromate and new added silver ions will form a brown silver chromate. So this is an indicator for when the solution turn from milky, well, approximately yellow milk, to with some extra brown precipitate, then you have the equivalence point. It's not so, it's easier to discuss when we are actually in the lab and doing the experiment. This is a way, if you know the concentration of the silver ions, and if you know how much sample water you have, this is a way to determine chloride ions. Similarly, here you have the original solution that is yellow from chromate. We add some chromate and then we add the silver ions to get some precipitate. But when this precipitate turn brownish, then we that is the point where we should read the Biuretton, have a look and do some calculations. This is also very quick experiment. It's something like 5 minutes, but it could perhaps be needed to be repeated a couple of times with different volumes and maybe different concentrations of the silver. I don't know. There will be large variations on the chloride ion concentration. For example, from the salt sea or the brackish salt water in the Värtan and the other lakes. So there is a large variation in volume that is needed. If you do get too small volume, you can always add some deionized water. That doesn't matter because that will only do the make it easier to handle the situation. Sulfates, very straightforward analysis. You should weigh approximately half a kilogram, half a liter of water, but weigh it carefully. Don't do an approximate weighing. I mean, we have a balance that gives weights in, say, 0.1 gram accuracy or something like that. And then you record that, make a solution of barium chloride and add that. Something like 2 grams of barium chloride is a heavy surplus. Adding that to the water will precipitate barium sulfate. And then maybe one should heat this sample water in order to get a more coarse precipitate. Otherwise, if it is very, very small particles, then it may pass through even a very fine filtration paper. There is also a possibility to do metal indicated titration, similar to calcium and magnesium, but the indicator is quite poisonous because it's an arsenic compound. So I did actually remove that. We don't do that. This is harmless. Finally, the oxygen determination. That this is exercise 1.3, I think. I have some pictures for that. Oxygen, gas in the water, dissolved oxygen, and we add manganese ions. Then in a basic environment, it produces, for example, MnO2 or Mn3 hydroxide or something like that. Some kind of oxidized species that are oxidized due to the fact that we have oxygen. And if manganese is in surplus, then the yield will be determined by the amount of oxygen. So if we can determine the amount of manganese oxide that is formed, that we can do at lab, we acidify the solution, add iodine, and then we will get some elemental iodine that is brown, and the amount will be dependent on the amount of manganese oxide, which is in its turn dependent on the amount of oxygen. So let's determine the amount of iodine, and this is brown. So adding thiosulfate solution will reduce the iodine to a colorless complex, and when the color has disappeared, then you can measure how much did I use. That is equal to the amount of iodine, which is equal to the amount of MnO2, which is equal to the amount of O2. Well, not maybe equal. These formulas, none of them are formally fully balanced. They need to be balanced. They are in the lab compendium, I think. Eventually, you may need to have some. You may want to have some starch, because then the iodine make a bluish complex. This is useful for indicating the end point, but don't add this starch from the beginning, because then it will be very blue, very blue, very blue, very blue, slightly less blue, and then colorless. But perhaps the starch will also make things less clear to the transition from iodine containing to iodide. It is said that this is necessary, but I don't agree at all. So it's as easy to see a brownish solution going colorless as it is for a blue complex going colorless. But maybe you don't agree, and then we can have a look at it. How does this manganese oxide form? Manganese, and then we go to basic, that is soluble, but in a basic environment, manganese 2 hydroxide would precipitate, but in the vicinity of oxygen in the solution, oxygen is stable above this dashed green line. So then, according to this diagram, either Mn3O4 or Mn2O3 or MnO2, that is the whole of this, MnO2 perhaps, will form. But the amount of the different phases, the total amount of them, the total amount of electrons removed from manganese is same as total amount of electrons that is consumed by the oxygen. This is approximately how complicated it gets, but I recommend you to try to understand this analysis. And finally, there is also a similar type of analysis, the permanganate number. Here we will, instead of measuring oxygen, measure amount of organic matter oxidized by, for example, permanganate or chromate. There are different methods that give slightly different results depending on what kind of oxidizing agent you use. I prefer permanganate because that is not at all as poisonous as the chromate. Manganese is essentially harmless compared to chromium. We have a permanganate solution with this concentration, and according to lab instruction, one should add, say, 4 milliliter of that to a sample of organic material, and hopefully the organic this is enough for oxidizing the organic material. If everything is consumed, this is visible actually by eye, because the permanganate is heavily colored. It's violet ion, and the reaction product, the manganese 2+ is colorless. So if the color disappears here, this 4 milliliter is too small an amount, then you need to repeat the experiment and with say 8 milliliters. I will see to that this solution is available. But let it oxidize the organic content, and after a while, if it's still violet colored, then you add iodine, then you produce elemental iodine, and we titrate this with thiosulfate, similar as we did for the oxygen determination. And then it's a lot of calculations. Well, a few calculations. You can use a formula, but I recommend trying to dwell into the details. We can have a discussion about this in the afternoon. The Porbert diagrams for iodine and manganese, they're shown here. The excess remaining permanganate ions mixed with iodide in an acid solution, what will happen? They don't occupy the same part. So permanganate will be reduced probably to manganese 2+, and the iodide solution will be oxidized to probably iodine. It's crystalline iodine here, but at low concentrations, iodine is soluble in water. And especially if you have a surplus of iodide ion, then this triiodide ion is formed. The triiodide is essentially a way to, this is quite low solubility of iodine, but if you add an iodide, then you will get this triiodide solution. And that is, since it is an ion, it is very soluble compared to non-charged species. Yeah, then we have lab 2. That is, we take that later. Questions? Discussions? What time should we gather tomorrow? Hello?
10 was fine.
What? What?
10 was fine. We can do it later if you want to, but it
Yep.
works.
Yeah, but what time was it?
At 10.
10 o'clock?
Yeah, you said so.
Yeah, I know. I just wanted to check. Now I know that you know, at least you, Eda. Okay. Any other questions from a chemical point of view?
Are we borrowing the lab codes and goggles?
Yeah.
Okay.
There are codes and Googles to borrow.
Okay.
Tomorrow you may not. Well, there is one risky moment tomorrow where we will add sodium hydroxide solution to a sample. I'll bring some Googles.
Do we need to do these Porbert diagrams for the lab report ourselves?
That's a good point. I never thought about that. You gave me the idea.
Oh no, I wish not. That was why I was asking.
Yeah.
Because I have a lot of problem like doing them correctly.
Yeah, but then perhaps on Thursday, do you have a laptop that you can bring? I'll show you.
Yeah.
Is it a Windows machine?
Yeah.
Yeah.
It is.
But then I'm sure that we can convince it.
Yeah, because for me it's like over, like this
Yeah,
do it digitally over Zoom, it's not working for my
no,
brain.
that I mean, it's far less efficient than actually doing it in real life. Yeah.
Yeah, thank you.
Yeah. Otherwise, should we have a lunch break?
Would be good.
Good, good, good.